Hello friends, so let's begin the lecture number 13 on advanced thermodynamics. So in the first 12 lectures we actually studied the laws of thermodynamics, the basic definitions that underlie these laws, and the laws of thermodynamics are actually presented using the Carrot-Tewedris formulation, which gives you a neat presentation without going back and forth on first and second laws. And we also showed at the end of the whole exercise that the laws that we derived using the new approach gave rise to the same concepts as the earlier approach, and it also actually helps us understand the concepts that we learned in the traditional approach in a little bit deeper and better fashion. Now, in the last lecture we said that from today onwards we'll be looking at equations of state, and I also defined equations of state as those that connect the generalized force, generalized coordinate and temperature. The equations of state actually are determined or dependent on the different kinds of interaction that are feasible in a given object. So in order to keep things simple, first let us deal with simple systems, which basically means that there will be only one mode of work interaction that will be feasible for a given object. So simple systems are those systems in which the number of work modes that is possible will be only one, and therefore there is one generalized force and one generalized coordinate that characterize that, and the relationship between that generalized coordinate, that generalized force and temperature gives you the equation of state. Now the second thing that we also need to understand about equation of state is that there is no simple single equation of state that characterizes given interaction. Let's take the example of water as a simple system. Okay, so water can, and let us look at only compression work, that is PdV work in water. So if I look at water in the different phases, so in gas phase at very low pressures it may be behaving like a gas, okay, and in the liquid phase it would be behaving reasonably incompressible. The density is a constant, so the PVT relationship, where V you can write volume per unit mass as a specific volume, which is the inverse of density, is reasonably invariant, and the pressure hardly plays a role. And same thing with solid. So depending on which phase we are in, the relationship between PV and T would vary, and in the regions where the phases coexist, where there is a liquid vapor equilibrium or a solid liquid equilibrium or solid liquid vapor equilibrium, the behavior would be entirely different, and therefore you possibly would need different forms of equations of state in the different regions of the pressure, volume, temperature regimes. Okay. So at some pressure and temperature it will behave like a solid, some pressure and temperature will behave like a liquid, some pressure and temperature will behave like a gas, and at some pressures and temperatures it has a combination of these, and in these regions of pressures and temperatures the equation of state for water needs to be different. The pressure, volume, temperature relationship between water needs to be different. So likewise, for elastic substances, for example, suppose I am looking at a rod which is being stretched. In the region where it is still within the elastic limits, where you leave the stretching and it goes back to its original length, the PVT relationship is something, but the moment it has crossed the elastic limits, then the force exceeds the force that is required to make it yield, or the stress exceeds the yield stress, then it has a completely different equation of state. So you can have different equations of state in different regimes of the generalized force, generalized coordinate regions, and similarly temperature. So higher the temperature, for example, the yield point might be different, and at lower temperatures the yield point might be different. So we have the possibilities of different PVT regions or different generalized force, generalized coordinate temperature regions in which there are different equations of state. So the equation of state also is not a single monolithic thing for a single substance, but also varies with the regimes. So it can have different equations of the same substance, the same material, same object can have different equations of state in different regimes of the generalized force, generalized coordinate, and temperature. And when there are multiple interactions that are possible in a given object, then one interaction might end up affecting the state of the object through possibly the temperature, and therefore the other, and therefore the interactions become more complex to study. So in this course we'll confine ourselves to simple systems, and more often than not we will be studying the compressible work. We will do a little bit of non-compressible systems. We'll look at systems which are other than compressible systems, let us say electric system, elastic system, etc. We'll look at small examples of those and how they are dealt with, but we will not go into too much detail of those, just to give a flavor that thermodynamics is a generalized subject, and the concept of first law, second law, equations of state, and so on can apply to all forms of interaction, is the message that we will be going through. Okay, so now the simple systems, therefore, the systems in which there is only one mode of work interaction that is possible. There is one generalized force and one generalized coordinate. And in addition to these work interaction, there is also a heat interaction possible, so interaction by contact, and that is related to the temperature, which is the driving force for the heat transfer. So the generalized force, generalized coordinate, and temperature are related, and now out of these three, only two would be independent, the third would be determined by the equation of state. So this is the characteristic of a simple system. A simple system with only one mode of interaction possible would have only two independent properties that determine its state, so long as it is in a pure phase, that is, there are no multiple components that are involved, and in a single phase, that is, there is no solid liquid phases, or there is no martensitic and austenitic or ferritic different phases. Though multiple phases are not involved and multiple components are not involved, so simple pure substance, single pure substance in one single state. So one state and one phase, then it's a pure substance in single phase. And this kind of a substance, when it's a simple substance, then it has only one work interaction possible and one thermal interaction possible. And characterizing these two, there are two independent variables that will uniquely determine its state. So that is the concept of simple systems. Now looking at simple compressible systems, it's the minus P, that is a generalized force, and a volume, that is a generalized coordinate. So it's P, V, and T. These are the three properties, out of which two of them will be related to the third using the equation of state. Right? So this is the concept that we will understand about simple compressible systems. Now, before going into details of the simple compressible systems, let's also look at some of the additional mathematical tools or equations that we can use from the laws of thermodynamics and generalized equation of thermodynamics that we derived in the previous lectures. So let's move to the whiteboard and try to understand these things. So we'll be dealing with simple compressible systems. Okay. So in simple compressible systems, we know from our combined first and second law that we derived in one of the previous classes, that we can write du is equal to Tds minus Pd. Okay, we had actually written dE is equal to Tds minus the summation of, or sorry, plus the summation of Fi dxi over all modes of interaction I that are feasible. Now in simple compressible system or simple system, there's only one I, and here Fi is minus P and dxi is dV. So this is your fundamental equation for thermodynamics for simple compressible systems. Okay. So now if I look at this expression as U being a function of S and V as the independent variables, because you have the ds and dv here. So then if I write du, that will be equal to del u by del s at constant v into ds plus del u by del v at constant s into dv. Okay. So now if I compare this equation with this equation, I'll find that T is the same as del u by del s at v, and minus P is the same as del u by del v at s. So you get T is equal to del u by del s at constant v, and minus P equal to del u by del v at constant s. Okay, so this is one set of properties that we get from this expression, and now we know that T is this and minus P is this, and I also know that if I have a function f, okay, del f by del x and del f by del y are known to me, then I also know that del squared f by del x del y is equal to del squared f by del y del x. Okay, so if I differentiate del f by del y by x and differentiate del f by del x by y, they should become equal. So now here in this case f is u and x and y are s and v. So I can write del squared u by del s del v is equal to del squared u by del v del s. Now here this is del by del s of del u by del v, and del u by del v is minus p, so this will be minus del p by del s, correct, is equal to, in this case this is del by del v of del u by del s, and del u by del s is t, so it is del t by del v. Okay, so this is one set of equations that we get from this fundamental equation for thermodynamics. What are the things that we get? We get the definition of T in terms of u and s and P in terms of u and s. This is, let's say, 1, and this is, let's say, 2, and in addition you get this relationship, which is 3. Okay, so this is one set of relationships that we get from this expression, the fundamental expression, which is du is equal to Tds minus Pdv. Now in addition, we define additional thermodynamic properties which are related to these quantities. We define the enthalpy H, which is U plus PV. In the most general case, H would be defined as U plus summation or minus rather U minus summation of F I xi summation over I. This would be the general definition of enthalpy. So if I had multiple work modes feasible, then this H would actually be contributed to by the internal energy as well as each of the combinations of generalized force and generalized quantity. Now for the simple compressible system, there is only one I, which is therefore the summation would go, and Fi is minus P and Xi is V, and therefore you get U plus PV. Okay, so then if I differentiate this, I get dH is equal to du plus P dV plus V dP, and we know du plus P dV from the previous expression, du plus p dv is TdS from here. So substitute that here, so this becomes TdS. So you get dH is equal to TdS plus VdP. Okay, so this is nothing but del H by del P, del H by del T first, into at constant P into dt, plus del H by del P at constant T into dP. Okay, so if I compare these expressions, T actually becomes equal to del H by del T, and V becomes equal to del H by del P. So that is the expression that we have. And then when we write del squared H by del T squared, del squared H by del P del T is equal to del squared H by del T del P, then differential of this with respect to P and differential of this with respect to T become equal, and that is the next expression. So the three equations that we would get here would be T is equal to del H by del P, what did I do here? Basically it's expression of S and P I have written in terms of T and P, so this have been, so del H by del S ds plus, so this is at constant P and this is at the constant S, right? So again here T is del H by del S at constant P, and V here is equal to del H by del P at constant S. So this is equation number 4, let me say. This is equation number 5, let me say. And then equation number 6 would be the cross derivative of this. So it will be del T by del P, okay, at constant S would be equal to del V by del S at constant P. This is the next expression that you would get. Okay, so this differentiated with respect to P would be equal to this differentiated with respect to S. So that is the expression that you get. This is equation number 6. Okay, so the same thing can be repeated for two other kinds of energies that are defined. One is the A, which is the Helmholtz free energy, which is defined as U minus Ts, and the other is the Gibbs free energy, which is G, defined as H minus Ts. So you get dA is equal to du minus T ds minus S dt, and du minus T ds from the original expression is minus P dV. So this is minus P dV. Okay, we'll write it in the next line. So this is equal to minus P dV minus S dt, which is also equal to del A by del V at constant T into dV plus del A by del T at constant V into dt. Okay, so you get the expression here, minus P is equal to del A by del V at T, and minus S is equal to del A by del T at constant V, and the cross derivatives, del P by del T, both are negative signs, so the minus sign will get cancelled. Del P by del T at constant V is equal to del S by del V at constant T. Okay, so this is the next expression that you get. is the next expression that you get. So you have the equation number 7, 8 and 9 here. The same thing we can replicate on this side. So dg would be equal to du or dh minus tds minus s dt. Okay, and in this case tds is dh plus v dp, so tds minus this will be v dp, this will be d dp plus or minus s dt. So this will also be equal to del g by del p at constant t dp minus or plus del g by del t at constant p dp. Now you can compare the terms and write v is equal to del g by del p at constant t and minus s is equal to del g by del t at constant p. And now using the cross derivatives, del v by del t at constant p is equal to del s with a minus sign, del s by del p at constant t. So this is then equation number 10, 11 and 12. So this is simple mathematical jugglery. We have actually defined 4 forms of the energy term. One is the internal energy, of course, U, which we already know of. We define enthalpy H, which is U minus the summation of generalized force into generalized coordinate. And for a simple compressible system, that comes out to H is equal to U plus PV. And using that, we derived 3 expressions. And then we defined 2 other quantities, the Helmholtz function. This is the Helmholtz function, or Helmholtz free energy we call it. The Helmholtz free energy, and this is the Gibbs free energy. Okay, or the Gibbs function. Now, in terms of internal energy and enthalpy, the Helmholtz function is U minus Ts and the Gibbs function is H minus Ts, and therefore you again get 2 other expressions by differentiating. dA is equal to minus PdV minus SdT and dG is equal to VdP minus SdT, and then you get this set of expressions. So from each equation we are able to derive one definition of the individual variables P, T, S and the pressure, volume, entropy and temperature, P, V, S and T. Okay, so in terms of P, V, S, T, we get the definitions of P, V, S and T in different forms in terms of the derivatives of these energy functions. And in the cross derivative form, we get 4 expressions in which one of the sides would be all measurable quantities and the other side would contain the entropy, which is a non-measurable quantity. So for example, let us look at equations 3, 6, 9 and 12. So equation 3 has del T by del V, which is here. This would be at constant S and this would be at constant V. So the del T by del V is actually obtainable if I have a PVT surface of substance measured. So I know the variation of PV and T with respect to each other. I should be able to evaluate at any given location the del T by del V when you go through an isentropic process, and that should be equal to del P by del S at constant V. In the same way, we can get in the next expression there is a del T by del P at constant S is equal to del P by del S. So the left hand side is all in terms of measurable quantities and the right hand side is in terms of entropy. The third expression again, del P by del T at constant V is in terms of measurable quantities and the right side is in terms of entropy. And here the del V by del T is in terms of measurable quantities and the next quantity is in terms of entropy. So you can actually get values for entropy if we define a datum at which the entropy becomes 0 using these derivatives. The values of entropy can be evaluated, and if I can relate internal energy, enthalpy, Gibbs function, Helmholtz function to the entropy and temperature pressure in some fashion, then we should be able to evaluate the other variables also. So these thermodynamic relationships come in very handy to construct property tables in terms of the quantities that are measurable and calculating the quantities that are not directly measurable in terms of the quantities that are measurable. Right? So that is the purpose. These equations 3, 6, 9 and 12 together are called the Maxwell relations. That's the name that is given to them. But the combination of these thermodynamic properties actually helps us in understand those. In addition, we also define a few quantities which are useful in thermodynamics. One is, of course, what is called the compressibility. Which is nothing but 1 by V or minus 1 by V del V by del P. Okay, and when this is done at constant temperature, you call it as isothermal compressibility, KT. And if it is done at constant entropy, that is minus 1 by V del V by del P. So the change in volume under the action of pressure at constant temperature is KT, and at constant entropy is Ks or kappa S. This is called the isentropic or adiabatic compressibility. Okay, so these two compressibilities are commonly defined. In addition to that, we have what is called the thermal expansion coefficient, which is 1 by V del V by del T, that is the change in volume under the action of temperature when it is constant pressure. So it is called the isobaric thermal expansion coefficient. This is normally denoted as beta, which is commonly used in heat transfer in particularly buoyancy driven flows. In addition to these, we have the specific heat Cp and Cv at constant volume, constant pressure and constant volume respectively, which basically are defined in terms of the specific internal energy and specific enthalpy, that is internal energy per unit mass or enthalpy per unit mass when they are changing with temperature. So Cp is defined as del H by del T at constant P, and Cv is defined as del U by del T at constant V. So these are quantities which are additionally defined, and they are also in terms of properties that are measurable and their derivatives. So these are also used in calculating one quantity from another in the thermodynamic property tables. Okay, so this is basically what I wanted to convey in this lecture. We'll pause at this in this lecture, and we'll continue in the next lecture with specifics of equations of state of various different forms for compressible systems. Okay, we'll stop here in this class and continue next.